Hello and welcome to this A-Level chemistry video about acids and bases, probably one of the largest and most important topics in physical chemistry. In this video, I'll cover the definitions of acids and bases, look at acid reactions and acid-base equilibria, and from there we'll move into pH calculations for strong acids, strong bases, using Ka values, using the ionic product of water, and look at the pH value calculations for mixtures. From there we'll move into focusing on pH curves and indicator action, and we'll finish by looking at buffer solutions, what they are, how they work, and how you calculate their pH. There are actually three different definitions for acids and bases that you need to be aware of, and we're going to look at them all here. The first one is the most important one for this topic, which is the Brønsted-Lowry definition. Acids are defined as proton donors or hydrogen ion donors, and bases are defined as something that can accept hydrogen ions or protons. And then Arrhenius acids are defined as acids that ionize when you put them into water, and that means that they dissociate and they produce hydrogen ions and something else. And bases will dissociate in water to produce hydroxide ions. And then the last definition is the Lewis acidity, and you need this more in the transition metals topic, really. But a Lewis acid is defined as an electron pair acceptor, and a Lewis base is an electron pair donor. Sometimes there might only be one of these definitions being satisfied by a situation, other times it could be two, or maybe even all three. Acids and bases can both be defined as being either strong or weak. Now, this is really different to concentrated or dilute. A concentrated solution just means that there is a large amount of solute dissolved in the solvent, whereas dilute means there's not very much. Strong means something quite different, and it's a measure of how fully the substance ionizes when you place it in water. A strong acid or base will fully ionize when you put them into water. And so that means that this reaction will go to completion. In contrast, a weak acid or a weak base will only partially ionize when you put it into water. And so that means that this reaction will not go to completion and it will be reversible. If we take a look at a few examples, strong acids are the ones that you've most commonly heard about, really. So hydrochloric acid, sulfuric acid, and nitric acid. And all three of these will dissociate, they will fully ionize in water, and that means this reaction will go through to completion. Strong bases, really, for A-level chemistry, encompasses anything that contains the hydroxide ion. So sodium hydroxide, potassium hydroxide, and barium hydroxide. Again, these will fully ionize. This reaction is shown as going to completion, and the arrow that we use represents that. For a weak acid, we're really talking about anything that is a carboxylic acid, so methanoic acid, ethanoic acid, etc. Since these only partially dissociate, we show these as equilibria, and we have the double-headed arrow in the middle to represent that. And the equilibrium will lie significantly to the left-hand side here. And last of all, weak bases. These really, there aren't many that you need to know for A-level chemistry, and the two that I would suggest that you remember are ammonia, and to link it to an organic chemistry topic, anything that's containing an amine functional group is likely to be a weak base. I'm going to outline a number of the different acid reactions that you need to be aware of from across the A-level chemistry course, and I'll pull them all together here. Firstly, and most commonly, acids react with bases to make a salt and water. And this salt will take its name partly from the base. Usually it will just be what is the metal present in the base, and then the other part will come from the different acid that we might use. And so hydrochloric acid will react with sodium hydroxide to produce sodium chloride and water. And if we were to use a carboxylic acid for an example, you would have ethanoic acid perhaps reacting with potassium hydroxide, and this would turn into potassium ethanoate salt and, of course, water. Now, if the carboxylic acid had a functional group at two ends, we had something called ethane dioic acid as an example, what would happen is the sodium hydroxide, for instance, that it's reacting with would react with both of those functional groups. And this would affect the balancing of the reaction. So we'd need two sodium hydroxide, and we would put a sodium at each of those ends, and we'd end up making two water molecules as a result. Acids can also react with metal oxides. When this happens, we still make a salt and water, and I'm showing an example of the equation here. When an acid reacts with a metal carbonate of some sort, we get a characteristic effervescence or fizzing being produced, and this is down to the production of carbon dioxide gas. This is, in fact, one of the tests that you need to know. It's a test for a carbonate ion. We can add an acid to it, and that fizzing means that we have got a carbonate ion present. Not only do we make the carbon dioxide, we make the salt and water in the same way that we saw in those other equations. The last acid reaction is when acids react with metals. When this occurs, because there is nothing else with the metal, we can only make a salt and hydrogen this time. There is nothing that's got the oxygen in that can allow us to make water. So magnesium reacting with sulfuric acid would make magnesium sulfate and hydrogen. Lots of acid-base reactions can actually be considered to be equilibria. If we reduce the reaction down to simply the passing of the proton between the acid and the base, we can see this more clearly. If we take this example that I've got here, where we've got the strong acid hydrochloric acid, it is going to donate a hydrogen to the ammonia. And it can do this because the ammonia, the nitrogen in the ammonia, has got a lone pair that it can use to accept that proton. Once this has happened, we produce the ammonium ion and the chloride ion. And ammonium is actually weakly acidic. And this makes sense because it's gained an extra hydrogen and it's now an ion, and so it has the potential to donate that proton back. And this chlorine has in fact got 4 lone pairs that it could use to accept that proton, and so this reaction is reversible. The equilibrium is likely to lie heavily to the right in this particular example, but it is potentially reversible. Because of this, we need to use some language about which acid we might be referring to, because there's an acid on both sides of the equation, and the same with the base. So the initial acid, the hydrochloric acid, is simply just referred to as the acid, and the ammonia simply the base. But the acid, once it has donated a proton, is taken to be a base. We call it the conjugate base because it is the base that goes with that acid. And similarly, the ammonia accepts the proton, and once it accepts the proton, we make the conjugate acid. And literally, we would define the conjugate acid as the species that forms once the base has accepted the proton. And so, in any acid-base equilibrium, there are always 2 conjugate pairs. You can actually get this when 2 acids react together. If we take the example of sulfuric acid, concentrated sulfuric acid, reacting with concentrated nitric acid in the reaction that generates the electrophile for the electrophilic substitution of benzene. Now, it seems weird these 2 acids are reacting together, but one of them is better at donating protons than the other. And in this case, the sulfuric acid is the stronger acid. It is the better proton donor, so it will donate a proton to the nitric acid. And you can see that that's happened because in the products, we've got the HSO4-, which is what forms when the sulfuric acid loses one of its hydrogen. And the HSO4- is the conjugate base that belongs to the sulfuric acid. And we make H2NO3+, which is the conjugate acid to go with the nitric acid, which was the base in the reactants. It's a really common question in A-level chemistry to calculate the pH of a particular solution. So what actually is pH? Well, the pH of a solution depends on the hydrogen ion concentration of that solution. The symbology pH actually means hydrogen ion potency. Now, you will remember, hopefully, that the lower the pH of a solution, that tells us that the acid is stronger. You can calculate the pH of a solution by taking the negative log of the hydrogen ion concentration of that solution. This is an incredibly important equation. And in fact, if a question asks you to define pH, they really just want you to give back this really important equation that's here in the form as I've written inside the box. The calculation is log to the base 10, but we don't normally write that 10 because we assume that when we're writing log log, that's what we mean. And if we mean something else, for instance, in the kinetics topic, we write ln for natural log. Since it's in the base 10, a difference of 1 in the pH means that the hydrogen ion concentration is 10 times bigger or 10 times smaller. So even a small change can be really significant. As a consequence of this, it's really important to report pH values to 2 decimal points, because even that second decimal point can be really significant when we're working with a log scale. So any calculation that requires you to calculate the pH of a particular solution is going to finish with the equation that I'm showing here, which means that the second to last step in the process is likely to be to find the hydrogen ion concentration. A question might come at this from the different angle, though. It might give you the pH of a particular solution and require you to then calculate the hydrogen ion concentration by rearranging the pH expression. So this gives us another equation that is not quite as important as the first one, but I'd be really surprised if you didn't use it at least once on an A-level chemistry paper. And that is that the hydrogen ion concentration can be calculated by using the inverse log of the pH. And what that is written as is it's 10 to the minus pH. And so you'll have to use the shift or the second function on your calculator and then type in the negative of the pH. And so, for instance, if we had a pH of 4.25, we could work out the hydrogen ion concentration by doing 10 to the power of minus 4.25, which gets us a hydrogen ion concentration of 5.62 times 10 to the minus 5. Since strong acids fully ionize in solution, this means that the moles of acid in that solution will be the same as the moles of hydrogen ions in that solution. Or, more usefully, the acid's concentration will be the same as the hydrogen ion concentration. And you can see that in these equations that I'm showing here. The moles of hydrochloric acid and hydrogen in the equation are the same. And so that means that if I had 1 mole of hydrochloric acid, I'll make 1 mole of hydrogen ions. And if I had 2 moles of nitric acid, I'd make 2 moles of hydrogen ions. We can see that those are going to be the same. And so this means if we're asked to calculate the pH of a nitric acid solution with a concentration of 2.20 moles per decimeter cubed, then we know that the hydrogen ion concentration will also be 2.20 moles per decimeter cubed. And so the pH is simply the negative log of that number. And so negative log of 2.20 is minus 0.34 to 2 decimal points. And I use this as an example to show you that the pH can be less than 1 and in fact less than 0. We could go the other way around. We could be asked to calculate the hydrogen ion concentration for hydrochloric acid that has got a pH of 1.85. And so this means that we can find the hydrogen ion concentration by doing 10 to the power of minus 1.85, which gives us an answer of 0.014, and this means that the hydrogen ion concentration is 0.014 and the hydrochloric acid concentration will be the same. Sometimes acids might contain more than one hydrogen ion that they can donate. A good example of this is sulfuric acid, and we say that this acid is diprotic to represent the fact that there are 2 protons that it can donate. And so you can see from the dissociation equation that for every 1 mole of sulfuric acid we have, we can get 2 moles of hydrogen ions from that. And we need to keep this in mind if we're calculating the pH of this acid. So for instance, if we're asked to calculate the pH of a sulfuric acid solution that has a concentration of 1.90 moles per decimeter cubed, this means that the hydrogen ion concentration will be 3.80 moles per decimeter cubed. In other words, double. And so the pH will be negative log of 3.8 rather than 1.9. And so this means that the pH will be negative 0.58 to 2 decimal points. And we need to keep this in mind in the other direction as well. So for instance, if we're asked what is the sulfuric acid concentration, if it has a pH of 0.65, we need to first recognize that hydrogen ion concentration is 10 to the negative pH, so 10 to the negative 0.65, which gives us 0.22 for the hydrogen ion concentration. But since the moles of sulfuric acid is half of the hydrogen ion concentration, we need to divide that by 2 to give us a sulfuric acid concentration of 0.11. Questions might sometimes ask us to find the pH of a solution of pure water. And to do that, we need to use something called the ionic product of water, which is given the symbol Kw. To understand this, we need to first recognise that in pure water, a small proportion of the molecules will ionize, and it will produce hydrogen ions and hydroxide ions. This is really only a slight dissociation, and so this means that the reaction is an equilibrium, as you can see from the symbol that I'm using here. Now the Kc, the equilibrium constant using concentrations, for this expression we'll have the products on the top, so hydrogen ion concentration and hydroxide ion concentration, and the water concentration on the bottom. Since this dissociation is only very slight, equilibrium lies heavily to the left-hand side, this means that the water concentration before equilibrium is reached will be pretty much equivalent to the concentration of the water at equilibrium. And so we can consider the concentration of water to be a constant value. And so if we put both of our constants on the left-hand side, you can see we've got Kc multiplied by the water concentration is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration. What we do in chemistry is the same as in maths. If you've got two constants in the same position, you combine them to get one. And this is the origin of the Kw value. And so you can see that Kw is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration, which is why it's called the ionic product of water. Those are the ions that came from the water. At 298 Kelvin, the value for the ionic product of water is 1 times 10 to the minus 14 mole squared dm minus 6. You'll usually be given this value, but you'll probably do so many questions that you will end up remembering it. For pure water, we know that the pH is 7, and we can prove this by rearranging the Kw expression. If water is pure, that means that we've only got water present, so that means that for every hydrogen ion that has been produced as a result of this dissociation, we will have a hydroxide ion as well. So those two concentrations are going to be the same. And so if we take out reference to the hydroxide ion concentration then and replace it with hydrogen ion concentration, you can see that Kw is equal to H plus squared. And so as a result of that then, the square root of Kw is equal to the hydrogen ion concentration. And so the square root of 1 times 10 to the minus 14 is 1 times 10 to the minus 7. And so that's the hydrogen ion concentration for pure water at 298 Kelvin. And so if we take the negative log of this value to find the pH, what we can see is this gives us a value of 7.00. And so we've proven that at 298 Kelvin, pure water has a pH of 7. If the temperature of water changes, its pH changes as a result. And this comes down to this dissociation equilibrium. The dissociation in the forwards direction involves the breaking of a bond. Breaking of bonds is always endothermic, and so the forwards reaction for this dissociation will be endothermic. And In an equilibrium, if you, for instance, raise the temperature, the equilibrium is going to shift to decrease that temperature. And so that means it will shift in the endothermic direction, which we've just said is to the right-hand side. As a result of this shift, that means the concentration of hydrogen ions is going to increase. And we know that that means that the pH will decrease. And so you can see that this will have an effect on the hydrogen ion concentration. It will also have an effect on Kw, since Kw is the product of hydrogen ions multiplied by hydroxide ions, or for pure water, Kw is H plus squared. If the hydrogen ion concentration increases, Kw must increase as well. And so what we can say is that as temperature increases, pH will decrease, and so the pH will be less than 7 if the temperature is greater than 298 Kelvin, and Kw will be greater than 1 times 10 to the minus 14 as well. And conversely, if the temperature is below 298 Kelvin, pH will be greater than 7, and the Kw value will decrease. Even though the pH has changed, though, we're still not in a situation where we've got acidic or basic conditions. And that's because that in pure water, the hydrogen ion concentration is the same as the hydroxide ion concentration. And so that means we are effectively neutral. We haven't got one of those bigger than the other. If we've got a question, it might ask us, what is the value for Kw if the pH is, say, 6.63? And we know that Kw is H plus squared, and so what we have to do is we have to work out what that hydrogen ion concentration is first. So we do 10 to the minus 6.63. This gives us a hydrogen ion concentration of 2.34 times 10 to the minus 7. And so when we square that value, we get 5.495 times 10 to the minus 14, or 5.50 times 10 to the minus 14 to 3 significant figures. We can calculate the pH of a strong base by utilising the value and the equation for Kw, because Kw is still a constant for a given temperature, even when we're not considering pure water. So Kw is the product of the hydrogen ion concentration multiplied by the hydroxide ion concentration, which means that if we know the hydroxide ion concentration and the value for Kw, we can find the H plus concentration and then negative log that to get the pH. So for instance, what is the pH of a 0.65 moles per decimeter cubed solution of sodium hydroxide at 298 Kelvin? Well, the fact it's at 298 Kelvin tells us that we can use Kw as 1 times 10 to the minus 14. Sodium hydroxide is a strong base, so that means that the hydroxide ion concentration is going to be the same as the sodium hydroxide concentration, so 0.65. And so what we need to do is 1 times 10 to the minus 14 is equal to H plus multiplied by 0.65. And so that means that the hydrogen ion concentration is 1 times 10 to the minus 14 divided by 0.65, which gives us a value of 1.5 times 10 to the minus 14. Then when we negative log this hydrogen ion concentration, we get 13.81 as our pH. And this works the same even if we've got a base that's got 2 hydroxide ion concentrations present. For instance, what is the pH of a 0.8 moles per decimeter cubed concentration of barium hydroxide? So first of all, we need to, again, recognise that it's a strong base, so that means that this will fully ionize, but this time for every 1 mole of barium hydroxide, there will be 2 moles of hydroxide, which means that the hydroxide ion concentration will be 1.6. And so the Kw divided by this hydroxide ion concentration gives us a hydrogen ion concentration of 6.25 times 10 to the minus 15, and then the negative log of this value gives us 14.20. The term POH doesn't normally appear on A-level syllabuses, but it can make your lives easier if you're confident with your maths to use the term POH. As a quick derivation, at 298 Kelvin, as we know, Kw is equal to hydrogen ion concentration multiplied by the hydroxide ion concentration. If we take negative logs of both sides of this expression, we get the negative log of Kw is equal to the negative log of H plus the negative log of hydroxide ion concentration. Now we know that the negative log of Kw is going to give us a value of 14 because Kw is 1 times 10 to the minus 14 at 298 Kelvin. The negative log of the hydrogen ion concentration is pH. The negative log of the hydroxide ion concentration is something called pOH. And so this gives us a really useful term of 14 is equal to pH plus pOH. Now, since pOH is negative log of the hydroxide ion concentration, what you can do is you can take a hydroxide ion concentration, you can take the negative log of it to get the pOH, and then you can subtract this pOH away from 14, and this gives you a value for the pH. And so, for instance, if we had a hydroxide ion concentration of 2.6, we can take the pOH of that gives us a negative log of 2.6. That gives us a pOH of minus 0.41. And then we can work out what the pH would be by doing 14 minus 0.41, which gives us 14.41 as the pH of this solution. This is quite a bit faster, but some people will prefer the KW method. Adding water to a solution will reduce the ion concentration, whether it's an acid or a base, and therefore the pH will change as a result of this. And so if you add water to an acid, the hydrogen ion concentration will decrease and the pH will increase. In other words, the solution will be less acidic. If you add water to a base, the hydroxide ion concentration will decrease, and therefore the pH will also decrease, and the solution will be less basic. This usually comes up in the context of strong acids, and that's where I'll focus for my example here, but it could be applied to other types of solution. An example question might be, what is the pH change if 20 cm cubed of 0.1 moles per decimeter cubed hydrochloric acid has 30 centimeters cubed of water added to it? Since we're being asked to work out a change, we need to know what the pH starts at. We're working with hydrochloric acid, which is a strong acid, therefore it will fully ionize in solution, and therefore the hydrogen ion concentration will be the same as the hydrochloric acid concentration, and so it will be 0.1. And pH is the negative log of the hydrogen ion concentration, and so this gives us a starting pH of 1.00 to 2 decimal points. We've added water to this hydrochloric acid solution, but this will not change the moles of hydrochloric acid present, since water is neither acidic nor basic. And so we can work out the moles that we have of hydrochloric acid by using moles equals concentration multiplied by volume, and so moles will be 0.1 multiplied by 20 divided by 1000, since volume needs to be in dm cubed. And so this gives us 2 times 10 to the minus 3 moles of hydrochloric acid before we added water, and this is still going to be the case after dilution. It's just that these moles will be dispersed over a larger volume of solution, because the new volume has increased to 50 cm cubed since we've added 30 cm cubed of water to our initial 20 cm cubed. And more usefully, we can say that this new diluted volume is 0.05 decimeters cubed. And so then we can work out the new hydrochloric acid concentration by doing moles divided by volume. So 2 times 10 to the minus 3 divided by 0.05 gives us a new diluted concentration of 0.04 moles per decimeter cubed. Hydrochloric acid is still a strong acid, it's just more dilute than before, so we can still say that the hydrogen ion concentration is the same as the hydrochloric acid concentration, and so we can work out the pH by doing the negative log of 0.04, and this gives us a pH of 1.40 to 2 decimal points. The question asked us for a pH change, and so the pH is changing from 1.00 to 1.40, and so this is a change of 0.40. Acid dissociation constants are given the symbol Ka, and they are numbers used to describe the strength of an acid in an acid-base equilibrium. In general, the stronger the acid is, the larger its Ka value will be. These values are based on the dissociation of the acid from the undissociated or unionized form into a proton and a conjugate base. In general, this dissociation can be represented by the equilibrium that I'm showing here, where I've got HA on the left-hand side, which is the undissociated acid, and on the other side of the equilibrium, we've got the proton, and I'm showing you this as A-, and this is the conjugate base. Sometimes it might be preferred to use HX and X- for the undissociated acid and its conjugate base, but typically HA is used. Some examples of Ka values, just to be representative, are for hydrochloric acid, 1 × 10⁷ moles per decimeter cubed. And since hydrochloric acid is a strong acid, we would expect a big number here. And for ethanoic acid, which we know is a weak acid, the Ka value is much smaller, as 1.7 × 10⁻⁵ moles per decimeter cubed. And in general, for monoprotic acid, the units for Ka are always going to be moles per decimeter cubed. You need to be able to write the expression for the equilibrium constant for a weak acid, and I'm going to show you how to do that here. First of all, if we consider the equilibrium where a generic acid, HA, reacts with water, we produce the hydronium ion and the conjugate base, represented by A-. The Kc for this expression would be expressed like this. We always have the product concentrations on the top and then multiplied together, and the reactant concentrations go on the bottom, again multiplied together. Now, to work towards the Ka expression, we need to recognize a number of assumptions. First of all, we're working with a weak acid. So this means that the water molecules are in a vast excess and they are only slightly ionized. And so that means that the water concentration will be approximately constant when compared with the water concentration before equilibrium was reached. And since the water concentration is constant, that means that we can move it up onto the left-hand side next to the Kc expression, and we can combine those together to produce one constant, which we call Ka. And then for simplicity, we replace the hydronium ion with H+. And so where we had the concentration of the hydronium ion on the top of the expression, we now have the H+ ion instead. And this is universally understood as the proton, regardless of its association with water, and it avoids unnecessary complexity in equations without changing their meaning. So the acid dissociation equilibrium is simplified down to the undissociated acid itself on the left-hand side and the hydrogen ion, or we might say the proton, and the conjugate base on the right-hand side. And so the Ka expression for this would be the hydrogen ion concentration multiplied by the A- concentration on the top and the undissociated acid concentration on the bottom. The second assumption that we need to make is that since we're working with a weak acid, very few acid molecules will dissociate, and so the acid concentration is effectively constant. And that means that the acid concentration that we knew when we made up the solution of the weak acid will be the same as the concentration of that weak acid once equilibrium has been reached, because such a small proportion of this acid has dissociated. And so that means that we can know the concentration of the weak acid and we can know the Ka for this acid, and this allows us to work out the pH at equilibrium. In order to do that, we also need to recognize that we're assuming that this weak acid is totally pure, which means that there are no impurities present, which means that since we have a 1-to-1 ratio of hydrogen ions and the conjugate base, we can say that the hydrogen ion concentration is equivalent to the A- concentration, and so we can actually amalgamate those terms on the top of the expression, and so we can have Ka equals H plus concentration squared divided by the concentration of the undissociated acid. It is really important to note, though, that if you are asked to give the Ka expression for a named acid, you must write the Ka expression in full, not one of these shorthand terms that I'm showing here, and certainly not the calculation aid, which is having the H plus squared term on top of the expression. To calculate the pH for a pure weak acid, we need to recognise the generic equilibrium for the dissociation of this weak acid and then construct the Ka expression. And this gives us Ka equals hydrogen ion concentration multiplied by A minus concentration divided by the undissociated acid concentration. And so to calculate the pH for a weak acid, we only need to know the Ka and the undissociated acid concentration. Remember, if you'd been asked to write the Ka expression for a named acid, you wouldn't use HA, you'd use the formula of that weak acid and of its conjugate base. And then we need to simplify this expression, recognizing that the hydrogen ion concentration is the same as the A minus concentration, and that gives us this simplified Ka expression with the H plus concentration squared on the top. And then we have a choice. We either substitute values in and then rearrange it and solve it, or we rearrange it to then substitute the values in later. If we choose to rearrange it, we get the hydrogen ion concentration squared is equal to Ka multiplied by the acid concentration, and this then gives us the hydrogen ion concentration, which can be found by taking the square root of Ka multiplied by the acid concentration. And then the final step, as with all pH calculations, is to do that pH is the negative log of that hydrogen ion concentration that we've just calculated. Let's take a look at an example now of how to calculate the pH of a weak acid. I'm starting with lactic acid, which has a concentration of 0.01 moles per decimeter cubed and a Ka of 1.287 times 10 to the minus 4 moles per decimeter cubed. The acid dissociation equilibrium shows the lactic acid formula on the left-hand side, and then hydrogen ions on the right-hand side, along with the conjugate base. The first thing I need to do is write the Ka expression, which is what I'm showing here. We have the hydrogen ion concentration and the conjugate base concentration on the top and the lactic acid concentration on the bottom. And then we simplify this expression because H plus concentration is equal to the conjugate base concentration. So that gets me the Ka equals hydrogen ion concentration squared divided by the lactic acid concentration. And then we're going to rearrange this. So I've got the hydrogen ion concentration squared equals Ka multiplied by the acid concentration. So substituting my numbers in, I have 1.287 times 10 to the minus 4 multiplied by 0.01. And so the hydrogen ion concentration squared is 1.287 times 10 to the minus 6. So I then need to square root this value that I've got here, and that gets me a hydrogen ion concentration of 1.13 times 10 to the minus 3 moles per decimeter cubed. And finally, I need to calculate the pH by taking the negative log of this hydrogen ion concentration, and that gets me a value of 2.95 for this pH to 2 decimal points. Values of Ka can be almost anything, from really huge, which means the position of this equilibrium is fully or almost fully to the right-hand side, so the concentrations of the product are huge, the concentrations of the reactants are small, which is why we get this huge Ka value. Or they can be very, very small, which means there is only very little dissociation, and the equilibrium lies significantly to the left-hand side, and that means that the number on the bottom of the Ka expression is very large, and those numbers on the top are very, very small. In the same way that we convert hydrogen ion concentration into pH, we can convert Ka values into pKa values, and this makes the numbers more manageable. And to do this, we show that pKa is equal to the negative log of Ka. And so that means if we have hydrochloric acid's Ka value of 1 times 10 to the 7, the pKa is the negative log of this value, which means the pKa is minus 7. And ethanoic acid's Ka of 1.7 times 10 to the minus 5, therefore the pKa is the negative log of this number, and that means that the pKa is 4.77. Do notice that these numbers for pKa don't have units, just like pH values don't have units. Also notice that the numbers are much more manageable and easier to understand and give meaning to than the really huge or really small Ka values are. They're much easier for us to comprehend. In the same way that you can switch between pH and the hydrogen ion concentration, you can actually calculate the Ka value from a pKa value. And to do that, you use the expression Ka equals 10 to the minus pKa. And so if we had a pKa of 3.75, the Ka would be 10 to the minus 3.75. And that means our Ka would be 1.78 times 10 to the minus 4 moles per decimeter cubed. And so in general, you need to know how to convert between Ka and pKa in either direction. And you also need to know the pattern of acidity, where a stronger acid will have a larger Ka value, but a smaller pKa value. pH curves show how pH changes during the reaction of an acid and a base. In this reaction, one chemical is added to another in a titration style experiment. And so you would have one chemical in the conical flask, I'm showing it as a weak acid here, and the other chemical would be in a burette. And for me, I've got a strong base in my burette. And to generate a pH curve, you would measure the starting pH with a pH meter, or you might call it a pH probe, and then you would gradually add more and more solution from the burette, swirling every time you add some solution and measuring the pH every time you add more of your solution from the burette. And you would add the solution in smaller amounts the closer you get to the equivalence point for this titration. And this will give you a picture of how the pH changes as you add more and more chemical from the burette. In an acid-base titration, the equivalence point is the point in the titration where the moles of H+ ions is equivalent to the moles of hydroxide ions. And so the base would have neutralized the acid in my titration example that I'm showing here. The end point for a titration is the point in the titration where the indicator changes color. And so this is an experimental observation. This topic is really, really important because it has links to 2 required practicals, or the practical assessed groups, depending on which course you are following. Firstly, in the titrations required practical, you need to be able to perform titration calculations and describe how to do a titration in the way that you learnt in the amount of substance topic. And in the pH curves required practical, you need to explain in great depth how you generate the pH curve itself. I go into greater depth about both of these in separate videos. You need to be able to sketch and explain the shapes of typical pH curves for all combinations of weak and strong monoprotic acids and bases. There are 4 that you need to know, and their precise shape depends on whether you are adding the acid to the base or the other way around. I'm going to start by showing you the curves where a base is being added to an acid. First of all, if we start with a strong acid in the conical flask, the pH will of course begin at a very low level because strong acids have got a low pH. If we add a strong base to this acid, the pH will of course increase. Once we reach the equivalence point, the pH increases sharply and very, very quickly. And then when we are finishing our titration, the pH is very high because we're adding a strong base, and strong bases have a high pH. The equivalence point then is this point here where we've got this vertical region of our pH change, and the pH at the equivalence point for a strong acid, strong base is 7. For a strong acid, weak base titration, again the pH starts low and it increases gradually until we reach the equivalence point. Again, I'm showing the equivalence point here, and then the pH changes rapidly and we finish with a pH that is not so high as before because we were adding a weak base to our strong acid, so we finish with the pH of a weak base. Do notice that the pH at the equivalence point, which is halfway up the vertical region at the equivalence point, and this will be less than 7, since the salt of the weak base is going to be a proton donor. And so that means that even though we have neutralized our strong acid, the salt that is produced is not actually precisely pH 7. This time, if we start with a weak acid and add a strong base to it, the pH will start low, but not as low as when we had a strong acid. And it will increase gradually until we reach the equivalence point. Then it will change quickly, it will increase rapidly, and it will level off at the pH of a strong base because the strong base has a high pH. Again, the equivalence point is where we see the rapid change in pH, and the pH at equivalence this time would be greater than 7, as the A- that is produced from the weak acid is actually a proton acceptor, and so this means at the equivalence point the pH will actually be greater than 7. And finally, if we take a weak acid and add a weak base to it, you can see that we start at the same pH as before, a below 7 pH, but not very, very low that you'd expect for a strong acid, and the pH increases gradually. We reach the equivalence point, and the pH changes from being an acidic point to a basic pH, so in other words, greater than 7, but there is no rapid change in pH at the equivalence point. But what we can say is that the pH at the equivalence point, you would expect it to be 7. When you add an acid to a base, you get 4 characteristic pH curves, and the shape of the pH curve for the particular titration depends on the relative strengths of the acid and the base. First of all, if you add a strong acid to a strong base, we obviously start with a high pH because of the strong base. Then when we reach the equivalence point, there is a rapid decrease in pH, and we finish with a very low pH because of the strong acid. The pH at the equivalence point is going to be 7 because we're using a strong acid and a strong base. When you add a strong acid to a weak base, the pH starts above 7, but not so high as the first example because we're only starting with a weak base. The pH decreases gradually, then we reach the equivalence point, and the pH decreases sharply to the pH of a strong acid. Notice at the equivalence point, the pH change is not quite so high as before because the pH wasn't as high as before already. And also note that the pH at the equivalence point is going to be less than 7 because the salt will actually be a proton donor. If we added a weak acid to a strong base, we again start with the high pH that decreases gradually. At the equivalence point, the pH change quickly decreases to the pH of the weak acid, and the pH at the equivalence point is going to be greater than 7 because the salt is going to be a proton acceptor. And finally, if we have a weak base and add a weak acid to it, the pH starts above 7, decreases gradually. At the equivalence point, there isn't really a sharp decrease in pH, there is just a point of inflection to the curve itself, and the pH at the equivalence point will be 7. Indicators are often weak acids that change colour based on the pH of a solution. This happens because they exist in equilibrium between two forms. First of all, we have the protonated form, which is typically shown as HIN, where H is the proton that the indicator could donate, and the IN is symbolising the rest of the indicator. And on the other side of the equilibrium, we have the proton that has been donated, and we have the IN-, which is representing the deprotonated form of the indicator. For something to be a suitable indicator, the protonated form and the deprotonated form of this indicator need to have different colours. At low pH, the solution has more hydrogen ions, and so the equilibrium will shift left and produce the protonated form of the indicator, and we will see that colour. As the pH increases, the hydrogen ion concentration will decrease, and so equilibrium will shift right and produce more of the deprotonated form, which has a different colour. Indicators change colour within a specific pH range based on their pKa. And the pKa for an indicator is the pH at which the concentration of the protonated form of the indicator and the deprotonated form of the indicator are equivalent. And typically, the pH range over which the indicator changes colour is its pKa plus or minus 1. In other words, it's approximately within 1 of their pKa. For example, phenolphthalein has a pKa of 9.4 and it changes colour between 8.3 and 10, so slightly less than 2 units wide. Similarly, methyl orange has a pKa of 3.7 and it changes colour over a narrower range, between around 3.1 and 4.4. While the exact range depends on the indicator, the plus or minus 1 rule is a helpful guide for understanding how indicators behave. When selecting an indicator for a titration, the best indicator to choose will be the one where the colour change, so that's the end point of the indicator, occurs during the rapid change in pH that occurs at the equivalence point. You need to be able to use pH curves to select an appropriate indicator. Now, importantly, the indicator that you choose needs to have a pH range that aligns with the rapid change in pH that occurs at the equivalence point. For instance, a strong acid, strong base titration has a very big change in pH at the equivalence point, between around 3 and 11. And so we need to choose an indicator that changes colour within this range. Two good examples that we could use are phenolphthalein and methyl orange. You can see that I'm representing the range over which these two indicators change colour, and both of these ranges align with the rapid change of pH that occurs at the equivalence point. For a strong acid weak base titration, you can see that the pH change is different. It is between 3 and 7. And so when we're choosing an indicator, the pH change of that indicator needs to fall entirely within that range. So of the two indicators that I've used previously, only methyl orange is appropriate because the pH range for phenolphthalein is too high. It's above that change in pH that occurs at the equivalence point. For a weak acid strong base titration, the pH change will be between 7 and 11 at the equivalence point. And so this time methyl orange would not be appropriate as its pH range at its endpoint falls outside the 7 to 11 range. Whereas phenolphtalene's endpoint coincides with this rapid change of pH at equivalence point, so it would be an appropriate indicator to use. For the pH curve for a weak acid, weak base, there isn't a rapid change in pH at the equivalence point, and therefore no indicator is suitable for this pH curve. You can see I'm showing phenolphthalein and methyl orange as definitely being inappropriate indicators, but even an indicator whose pKa was 7 would still not be appropriate because of that absence of a sharp, rapid change in pH at the equivalence point. The pH change would still begin before the equivalence point and finish after the equivalence point. And so the indicator would change colour over a range of different pH values and over a range of different volumes of base being added to the acid. In a titration, a base, for example sodium hydroxide, is added from a burette and reacts with a weak acid, HA, which is in a conical flask, and the acid is turned into the salt, A-, and water. Remember that the equivalence point in an acid-base titration is where the moles of hydrogen ions is equal to the moles of hydroxide ions. In other words, at this point, all of the acid has been neutralised and converted into A-. If 20 centimetres cubed of base is needed to react with all of the weak acid, it follows that 10 centimetres cubed of base would be needed to react with half of that weak acid. This is known as the half-equivalence point. And at this point in a titration, precisely half of the acid has been used up and converted into the salt, A-, and half of the acid is left unreacted in the conical flask. And this means that the concentration of unreacted acid, HA, is exactly equal to the concentration of the salt that has been produced, A-. The Ka expression for this weak acid will have Ka equals hydrogen ion concentration multiplied by salt concentration divided by unreacted acid concentration. And since the unreacted acid concentration is the same as the salt concentration, these terms will cancel out in the expression. And so it will simplify down to Ka is equal to the hydrogen ion concentration. And then if we take negative logs of both sides of this expression, the negative log of Ka is equal to pKa, and the negative log of the hydrogen ion concentration equals the pH. And so we can say that at the half equivalence point, Ka is equal to the hydrogen ion concentration, and pKa is equal to pH. You can carry out an acid-base titration in order to identify an acid using the half equivalence point. You would do a titration once with an indicator and use the indicator's colour change to work out the volume of base added to fully neutralise the acid at the equivalence point. For instance, we might find 20 centimetres cubed of base was needed to neutralise the acid. And then you'd repeat the titration, only this time you'd add enough base to precisely half neutralise the acid. So for my example, this would be 10 centimetres cubed. And then at this point you would use a pH probe, or you might call it a pH meter, to measure the pH at the half equivalence point. And at this point, since the concentration of unreacted acid is precisely equal to the concentration of base that has been produced, Ka is equal to the hydrogen ion concentration. And so if we take negative logs of each of these terms, we get negative log of Ka equals negative log of the hydrogen ion concentration. And negative log of Ka is pKa, and negative log of hydrogen ion concentration is pH, and therefore pKa equals pH. And so we can say that the pH at the half equivalence point is equal to the pKa of the acid. And since acids have a specific pKa value, this value can be used to identify the acid. A common task in A-level chemistry is to be asked to calculate the pH of a mixture. For instance, in the situation that I'm showing at the bottom of the screen, where we're told that 20 cm cubed of strong acid, with a concentration of 0.1 moles per decimeter cubed, is added to 30 cm cubed of strong base, also with a concentration of 0.1 moles per decimeter cubed. And we're tasked with finding out the pH of the mixture. And of course, the pH of the mixture will be different to the pH of the separate solutions. And when these chemicals react together, one of them will get used up, that's the limiting reagent, and the other will be present in excess. And the method that you use to find the pH will vary depending on which of the two chemicals is in excess. Since we're being asked to find out the pH of this solution, the final step will always be the same, regardless of which chemical is in excess. We will need to do pH equals negative log of the hydrogen ion concentration. And so that means all of the previous steps will be working towards finding out what this hydrogen ion concentration is. The first few steps of this process are always the same, regardless of which chemical is in excess. Firstly, we need to calculate the moles of acid and the moles of base that we have at the start of this experiment. And this is most likely going to be done using the equation moles equals concentration multiplied by volume. And then it's worth looking at the formulae of the acid and base involved to see whether the acid is capable of donating more than one hydrogen ion, or the base is capable of donating more than one hydroxide ion. And if that is the case, we would need to scale that up by perhaps doubling the moles of acid to get the moles of H+, for instance. This step is not necessary for a weak acid, since weak acids only partially ionize. And then the next step is to compare the moles of hydrogen ions to the moles of hydroxide ions in order to determine which of the two is in excess, because this influences which of the pathways we then follow. The first of our three pathways is followed if we have a strong acid in excess. And this is the easiest pathway since strong acids fully ionize and we know the excess hydrogen ion moles. And so it's just that these moles are now spread out over a larger volume. And so step 4 on this pathway is to work out the new hydrogen ion concentration by taking the excess moles of hydrogen ions and dividing it by the new volume, which must be in decimeters cubed. And the new volume will just be the sum of the two individual volumes of the solutions that we reacted together. And then having got this hydrogen ion concentration, we would negative log that to find the pH. If we had a strong base that was in excess, step 4 here is also to find out the concentration of the excess ions. Of course, these are hydroxide ions, so we would take the excess moles of hydroxide ions, divide this by the new volume, again in decimeters cubed. And having got the hydroxide ion concentration, we then calculate the hydrogen ion concentration by rearranging the Kw expression. And so this gives us hydrogen ion concentration is equal to Kw divided by the hydroxide ion concentration. And then as a final step for this pathway, we would take the negative log of this hydrogen ion concentration that we've just found out. Perhaps the most difficult pathway is when we have a weak acid that is present in excess. Obviously, with it being a weak acid, we need to use the Ka expression to find the hydrogen ion concentration. And so the hydrogen ion concentration is equal to the Ka multiplied by the undissociated acid concentration divided by the conjugate base concentration. And in this case, the units are going to cancel out for this term on the right-hand side because we're taking one concentration and dividing it by another. And this means it's okay to use moles. So I've rewritten the expression with H plus concentration is equal to Ka multiplied by the excess Ha moles and divided by the A minus moles. Now the excess moles of acid, which we calculated at an earlier step, is easy to find. But the mistake that people often make is with the A minus moles. And the way that we find out the moles of A minus that have been produced is by looking at the moles of base that we used in the first place, or the moles of OH minus more precisely that we used in the first place, because the moles of conjugate base that we produce is going to be equal to the moles of hydroxide used. And so it's this term that we substitute in to our expression to find the hydrogen ion concentration. And you'd probably get a mark for this pathway for stating that the moles of A minus is equal to the moles of OH minus used. And then, having got this H plus concentration, our final step is to work out the pH by taking the negative log of this value. Calculate the pH of the solution formed when 50 centimeters cubed of 0.1 moles per decimeter cubed sulfuric acid is added to 30 centimeters cubed of 0.15 moles per decimeter cubed sodium hydroxide. The first step is to work out the moles of the acid and the base. Firstly, for the sodium hydroxide, moles equals concentration multiplied by volume. Concentration is 0.15 and the volume in dm cubed is 0.03. This gives us 0.0045 moles of sodium hydroxide. And since there is one hydroxide ion in each mole of sodium hydroxide, the moles of sodium hydroxide will be the same as the moles of the hydroxide ion. And then for the moles of sulfuric acid, moles again is equal to concentration times volume, so 0.1 times by 0.05 gives us 0.005 moles of sulfuric acid. Sulfuric acid is a diprotic acid. That means it has two replaceable hydrogens in its structure, so that means that the moles of the hydrogen ions will be double the moles of the acid. So we need to multiply that 0.005 by 2 and we get 0.01 moles of hydrogen ions. This then gives us an excess of hydrogen ions because 0.01 is greater than 0.0045. Quite how much is in excess we have to calculate. So the excess moles of hydrogen ions is the moles of hydrogen ions, 0.01, minus moles of hydroxide ions, 0.0045. This gives us 0.0055 moles of hydrogen ions. We need to then work out the new hydrogen ion concentration by dividing this excess moles by the new volume, which is 50 cm cubed plus 30 cm cubed, so 0.08 dm cubed. Once we've done that, we get a concentration of 0.06875. We then need to take the negative log of this answer to find the pH, and this gives us a pH of 1.16 to 2 decimal points. Calculate the pH of the solution formed when 25 centimeters cubed of 0.25 moles per decimeter cubed hydrochloric acid is added to 100 centimeters cubed of 0.2 moles per decimeter cubed sodium hydroxide. First of all, calculate the moles of sodium hydroxide by taking the concentration, 0.2, and multiplying it by the volume, 0.1. That gets us 0.02 moles of sodium hydroxide and the same moles of hydroxide ions. Moles of hydrochloric acid is its concentration, 0.25, multiplied by its volume, 0.025. That gets us 0.00625 moles of hydrochloric acid. This will be the same as the moles of hydrogen ions. Notice here we have no diprotic acid or no dibasic base, but it's always worth taking the time to check those formulae. So the moles of hydroxide is in excess because 0.02 is greater than 0.00625. Quite how much in excess? We have to subtract the 0.00625 away from 0.02, and that gets us 0.01375 moles of excess hydroxide ions. We then need to calculate the new hydroxide ion concentration by taking this excess moles value and dividing it by the new volume. So 100 cm cubed plus 25 cm cubed is 0.125 dm cubed. When we run this calculation, we get a hydroxide ion concentration of 0.11 moles per decimeter cubed. Since Kw is hydrogen ion concentration multiplied by hydroxide ion concentration, the hydrogen ion concentration is equal to Kw divided by the hydroxide ion concentration. And so we need to do 1 times 10 to the minus 14 divided by 0.11, which gets us 9.09 times 10 to the minus 14 moles per decimeter cubed. pH is negative log of this hydrogen ion concentration, and so that gives us a pH of 13.04 to 2 decimal points, proving that our strong base is present in excess. Calculate the pH of the solution formed when 30 centimeters cubed of 0.25 moles per decimeter cubed ethanoic acid is added to 20 centimeters cubed of 0.2 moles per decimeter cubed sodium hydroxide. Ka is 1.7 times 10 to the minus 5. This is a big clue that the weak acid is going to be found to be in excess, and so therefore we will need to use the Ka value. So the moles of sodium hydroxide is the concentration, 0.2, multiplied by the volume, 0.02. That gives us 0.004 moles of sodium hydroxide and 0.004 moles of hydroxide ions. The moles of ethanoic acid is the concentration, 0.25, multiplied by the volume, 0.03, which gets us 0.0075 moles of ethanoic acid. Now, since ethanoic acid and sodium hydroxide react in a 1-to-1 ratio, it's nice and straightforward to work out what the excess will be. 0.0075 is greater than 0.004. That means the weak acid is present in excess. So we take that moles of weak acid and subtract the moles of hydroxide ions away from it. So 0.0075 minus 0.004 gives us 0.0035 moles of weak acid, the ethanoic acid in this example. Then we need to recognise that the moles of A-, so that is the salt, that is produced will be equal to the moles of hydroxide ions that were used up in this reaction. And so that will be 0.004 moles of A- present in our product. Then we need to recognise that we have an excess moles of weak acid, so we need to use that Ka expression as we predicted. We need to find our hydrogen ion concentration. So we take our Ka value, 1.7 times 10 to the minus 5, we multiply it by our excess moles of HA, 0.0035, and divide it by our moles of A- that has been produced, 0.004. This gives us a hydrogen ion concentration of 1.4875 times 10 to the minus 5 moles per decimeter cubed. And then pH is the negative log of this hydrogen ion concentration that we've just calculated, and so the pH of this weak acid in excess reaction mixture is 4.8. 0.83 to 2 decimal points. Buffer solutions are designed to resist slight changes in pH when small amounts of acid, base, or water are added. There are a variety of different uses for buffers, but what they all have in common is that the buffer solution is used to maintain pH levels. For instance, when we're standardizing pH meters, or if we are carrying out a biological systems reaction, for instance, fermentation, or if there's an enzyme-controlled reaction and we want to provide the optimum pH for enzyme activity, or if the enzyme may become denatured in extremes of pH. They're also used to maintain the pH in shampoos and cosmetics. There are two types of buffer solution. There are acidic buffer solutions, and these maintain the pH at a level below 7, or a basic buffer solution, which have a pH of greater than 7. An acidic buffer has two parts: a weak acid, for instance ethanoic acid, and a strong conjugate base salt of that acid, for instance sodium ethanoate. Basic buffers also have two parts. For instance, the weak base part will be ammonia, and the strong conjugate acid salt of that base would be, for example, ammonium chloride. The precise chemical reactions that occur when buffers act to resist that change in pH will vary depending on the chemicals that are in that buffer. But in general, buffers maintain the pH since they contain two crucial components. First of all, a proton acceptor that can react with any added acid. And so this would be the weak base in the case of a basic buffer, or the strong conjugate base salt in the case of an acidic buffer. And buffers also contain a proton donor that can react with any added base. And so this would be the weak acid if we're using an acidic buffer, or the strong conjugate acid salt in the case of a basic buffer. And I keep referring to a strong salt, and like a strong acid which fully dissociates into ions in aqueous solution, a strong salt will also fully dissociate into ions, and therefore there will be a high concentration of the ions. So in the case of sodium ethanoate, that will fully dissociate into ethanoate ions and sodium ions, and so there will be a high concentration of those ions. And the salt ammonium chloride will fully dissociate into ammonium ions and chloride ions, again giving us a high concentration. And so for an acidic buffer, for instance, this would contain lots of unionized weak acid, for instance ethanoic acid. It would also contain lots of negative ions from the strong conjugate base salt, and this would be, for instance, ethanoate ions. And additionally, the buffer will contain enough hydrogen ions to make the solution acidic. Acidic buffer solutions have a pH of less than 7, and they are made from a weak acid and a salt of that weak acid. For example, we could have ethanoic acid and sodium ethanoate. And so this buffer solution will contain a proton acceptor that can react with the added acid. And so if we added hydrochloric acid, for instance, those hydrogen ions from the hydrochloric acid will be removed from the buffer solution by them combining with the negative ion from the salt, so the ethanoate ion here. And we would produce ethanoic acid as a result of this reaction. And then if we added a base, for instance sodium hydroxide, this buffer solution contains a proton donor that will react with it. And so in this case, the extra hydroxide ions from the added base are removed because they combine with the hydrogen ions from the dissociation of the weak acid. And this will produce water. And then remember that ethanoic acid is a weak acid, so it will have a dissociation equilibrium, and that equilibrium position will lie to the left-hand side. And since the hydrogen ions are used up, the acid equilibrium shifts to the right, i.e. more ethanoic acid will dissociate in order to replace the hydrogen ions and therefore to maintain the proportion of those ions. pH curves can be brought into questions about buffer solutions in two particular ways. The first one would most likely take the form of a multiple choice question, and it could quite simply ask you at which point in the titration is a buffer solution present, and they might give you 4 options, A, B, C and D, in the way that I'm showing here. And what you would need to do here is pick the correct answer, which is B. In this region, we will have a buffer solution present. A more detailed question might ask you to explain this part of the graph or to explain why there is a buffer solution present at this point. Well, first of all, if we explore the beginning of the reaction, there is only weak acid present at the start, so there is a low pH, but there is no buffer solution present. But as the reaction proceeds, the weak acid reacts with the strong base to produce a salt and water. And so what we see during the titration is the pH increases reasonably rapidly for a short period of time, but then the gradient begins to get more gentle as the pH change is resisted. And that's because in this region of the pH curve, we have got some unreacted weak acid, because only some of it has been used, and we have got some salt of that weak acid. And so those are the two key components of a weak acid buffer solution. And so therefore, the pH change is more gradual until we get close to the equivalence point, and then once all of that weak acid has been used up, we will have the rapid change in pH as you would expect for the titration. But during this period of the graph, there is very little change in pH, even though we are adding a strong base to the solution. By far the most common basic buffer involves ammonia as the weak base and ammonium chloride as the salt. And this strong salt fully dissociates into ammonium ions and chloride ions. So this basic buffer would contain lots of unreacted ammonia, lots of ammonium ions from the salt. And since ammonia is a weak base, it will have an acid-base equilibrium with water. And the position of this equilibrium will lie heavily to the left-hand side, but there will still be enough hydroxide ions to make the solution basic. In other words, have a pH greater than 7. And so this buffer contains a proton acceptor that can react with any added acid. And so if we added hydrochloric acid, the hydrogen ions from that acid would be removed by combining with the hydroxide ions from the equilibrium that I've already mentioned. This would have the effect of decreasing the hydroxide ion concentration. And so the equilibrium position would shift to the right-hand side to replace those hydroxide ions to a level similar to what it was before, and therefore the pH will stay approximately the same. This buffer also contains a proton donor that can react with added base. And so if we added sodium hydroxide, the hydroxide ions that had been added would react with ammonium ions from the salts. And so the added base does not raise the pH because the equilibrium will shift to the left-hand side on this occasion to restore the hydroxide ion concentration to close to its original level. You need to be able to calculate the pH of buffer solutions, and for most exam boards for A-level chemistry, we'll be calculating the pH of weak acid buffer solutions. So our final answer will have a pH of less than 7. Since we're calculating the pH of a weak acid, we need to use the Ka expression, where Ka equals H plus ion concentration multiplied by A minus ion concentration divided by the undissociated acid concentration. Now, since we're not working with a pure weak acid, we cannot use the simplification where the hydrogen ion concentration is equal to the A minus ion concentration. This will not be the case. And so that means that we cannot approximate our expression to be Ka equals H plus squared over HA because we're not dealing with a pure weak acid. And so since we're calculating the pH of our buffer solution, we need to find our hydrogen ion concentration. So we rearrange the weak acid expression to give us Ka multiplied by HA concentration divided by A minus concentration gives us the hydrogen ion concentration. Or if we write it slightly more tidily, Ka multiplied by HA concentration over A minus concentration equals H plus concentration. And I do this to show that the hydrogen ion concentration and the pH, therefore, depend on the ratio of HA concentration to A minus concentration. And so that means that a concentration of 4 and 2 would give us the same pH as concentrations of 14 and 7, even though the amounts of substance are significantly different. The pH would be the same for both of those circumstances. And this is also why adding water does not change the pH of our buffer, because diluting a buffer will affect the HA concentration and the A minus concentration equally, and so therefore the pH will be unchanged. From the point of view of the equilibrium for the buffer, we could also say that adding water will give us some extra hydrogen ions and hydroxide ions in equal proportions, and so the equilibria will shift an equal amount in both directions. And so, if we're calculating the pH of our buffer, step 1 will always be to use the Ka expression to calculate the hydrogen ion concentration. And then step 2 will be to calculate the pH by using the equation pH equals negative log of hydrogen ion concentration. The easiest example of a buffer pH calculation is when they give you the concentrations of the two crucial ingredients for the buffer along with the Ka. And so a question might say, a buffer solution contains 0.2 moles per decimeter cube concentration of methanoic acid and 0.3 moles per decimeter cube concentration of sodium methanoate, which is the salt, and they ask you what is the pH, and they give you the Ka for the weak acid. And so we have to use the rearranged Ka expression that I've got at the top of the screen, and then we substitute the numbers in, and we get H plus equals the Ka, 1.6 times 10 to the minus 4, multiplied by the HA concentration, 0.2, divided by the salt concentration, 0.3. And remember, we're showing that as a ratio because that is the crucial component. And then we get an H plus concentration of 1.067 times 10 to the minus 4 moles per decimeter cubed. And since we've been asked to find the pH, we need to then take the negative log of this hydrogen ion concentration, and we get a pH of 3.97 to 2 decimal points. You could be expected to calculate the pH of a buffer solution when given concentration and volume values for the chemicals and the Ka for the weak acid. To do this, the first step is to calculate the moles of the weak acid and the moles of the salt. To do this, we use the equation moles equals concentration times by volume, and we need to remember that the volume needs to be in dm cubed for this, and so since in my question here I've given the volumes in cm cubed, we need to remember to divide those by 1000. Now, we can't just go ahead and use the concentration values here. We have to work out the moles because we've got different volumes of each of these solutions. If they were the same volume of each solution, we could in fact just use the concentration values. So for the ethanoic acid, the concentration is 0.15, and we need to multiply that by the volume of 0.02 to get 3 times 10 to the minus 3 moles of our weak acid. And then for the salt, the concentration is 0.25 and the volume is 0.03, and so the moles is 7.5 times 10 to the minus 3 moles of our sodium ethanoate. And we can tell from the name, because it ends in anoate, that this is the salt of the weak acid. So this is our A- moles. For buffer calculations, you can actually use moles values instead of concentrations, as the units will cancel out. And remember that moles is proportional to volume, and it's the ratio that is the key here for the weak acid to the salt concentration, or the weak acid to the salt moles. So we can substitute moles into the rearranged Ka expression. So the hydrogen ion concentration is Ka 1.74 times 10 to the minus 5 here, times by 3 times 10 to the minus 3 moles, divided by 7.5 times 10 to the minus 3 moles. So H plus concentration is 6.96 times 10 to the minus 6 moles per decimeter cubed. Now we've been asked for a pH value, so we need to take the negative log of this hydrogen ion concentration, and that gets us a pH of 5.16 to 2 decimal points. When an excess of weak acid is reacted with a strong base, a buffer solution can be produced, and you need to be able to work out the pH of the resulting weak acid buffer solution. And so in general, weak acid, which I'm showing here as HA, reacts with a base, for instance sodium hydroxide, to produce the salt, in this case NaA, which is effectively A minus, remember, because it's a strong salt, and also water is produced. And when these react together, some of the weak acid will be used up, all of the base will be used up because the weak acid is in excess, and salt and water will be produced. Now the water produced is not relevant, but what is relevant is the A minus that is produced. Since all the coefficients in the equation are 1, however many moles of strong base are used, that will be the moles of salt that are produced. And there is often a mark in an exam question for recognizing this. So it's always worth stipulating that you've calculated the moles of sodium hydroxide used, for instance, and that will be the same as the moles of the salt formed. You need to be able to recognize that a reaction is occurring, and one of the clues will come from the name. We're using sodium hydroxide here, which is a strong base, and that will react with the weak acid, as opposed to if we had something like sodium ethanoate, and that would just mix with the weak acid. So the hydroxide is the crucial part of the name that tells you that a reaction is occurring. For a specific example, if we had ethanoic acid and sodium hydroxide, we know that they would produce sodium ethanoate and water. And you might be asked to calculate the initial moles of the sodium hydroxide and the ethanoic acid. I'm going to assume that we've done that and say that we're starting with 8 moles of ethanoic acid and 2 moles of sodium hydroxide. And you won't be told anything about the salt, but we'll assume that there is none, and the water, remember, is not relevant. Of course, since the sodium hydroxide is the smaller number of moles, it will all get used up in this reaction. And so the change in moles of the two reactants is 2. Both of these will go down by 2, and so at the end we will have 6 moles of our weak acid and 0 moles of our strong base, because it's all been used up. But the moles of strong base is equivalent to the moles of salt that's formed, so that will go up by 2 in this case, and we will have 2 moles of A minus at the end of this reaction. And then to calculate the pH, don't forget that moles is proportional to concentration, and the units are going to cancel out, so we can use moles values in our Ka expression. And so the rearranged Ka expression is shown here, and so therefore the H plus ion concentration is equal to the Ka, which is 1.74 times 10 to the minus 5 for ethanoic acid, multiplied by the moles of the weak acid, which is 6, divided by the moles of the salt, which is 2. And then this gives us a hydrogen ion concentration of 5.22 times 10 to the minus 5 moles per decimeter cubed. We've been asked to calculate the pH of the resulting buffer solution. The pH is negative log of the hydrogen ion concentration, so negative log of 5.22 times 10 to the minus 5, which gives us a pH of 4.28 for this buffer solution. You could be asked to calculate the pH of a buffer solution after something has been added to it. And of course, what will happen is the quantities of salt and weak acid will change slightly as a result of this addition. And so if we add base to a buffer solution, for instance sodium hydroxide, remember the hydroxide ions are the crucial component of this base, the hydroxide ions will react with the weak acid from the buffer, and this will produce water and, crucially, our salt A-. And so as a result of this reaction, the weak acid moles will decrease and the A- moles will increase. If we added an acid to this buffer, for instance hydrochloric acid, effectively we're adding hydrogen ions here. Just watch out for this being monoprotic or diprotic. And the hydrogen ions from the acid will react with the salt from the buffer and we will produce weak acid. So that means that the A- moles in the buffer will decrease and the HA moles in the buffer will increase. And so we can quantify this by looking at what is being added in more detail. So if we, for instance, started with 3 moles of weak acid in our buffer solution initially and 3 moles of our salt in the buffer initially, and then we added some sodium hydroxide to it, we add Z moles of sodium hydroxide, just to not use any particular number, we are effectively adding Z moles of hydroxide. This, remember, will react with the acid component of the buffer, and so therefore the quantity of acid is going to decrease, and it will decrease by Z moles. So after the addition of our sodium hydroxide, we will have 3 minus Z moles of the weak acid, and the salt is produced. In other words, A minus moles is going to increase, and so we will end up with 3 plus Z moles of A minus. If we were to add X moles of hydrochloric acid to our buffer, in other words, X moles of hydrogen ions, this would react with the A minus in the buffer, so the A minus moles will go down, and it will react in a 1-to-1 ratio, so after this addition of X moles of hydrogen ions, we will have 3 minus X moles of our A minus in the buffer solution. And that will produce the weak acid, remember, and so after the reaction, we will have 3 plus X moles of weak acid. In other words, the moles of weak acid are going to increase by the moles of hydrochloric acid added. Remember to be careful, if we had a diprotic acid, we would be adding double the moles of H plus that we were adding weak acid. And if it was something like barium hydroxide with 2 hydroxide ions, we'd need to factor that in as well. Buffer solutions maintain an approximately constant pH, but the pH may change slightly, and they will become saturated if too much acid or base is added, and then the pH would change significantly. And you could be asked to calculate the pH of a buffer solution after something has been added to it. And so, for instance, if we say that we have a buffer solution containing 6 moles of ethanoic acid and 2 moles of sodium ethanoate, and then 0.5 moles of sodium hydroxide is added to the buffer solution, we could be commanded to calculate the new pH value when given the Ka for this weak acid. And what we need to recognize is that the added sodium hydroxide will react with the weak acid component of this buffer and produce salt and also water. And so if we set out our equation showing that we've got 6 moles of ethanoic acid and 2 moles of our salt, sodium ethanoate, and acknowledge that we are adding 0.5 moles of sodium hydroxide to this buffer solution. The 0.5 moles of sodium hydroxide is of course all going to get used up, but when it gets used up, it will use up an equivalent number of moles of our weak acid, ethanoic acid. And so therefore, the moles of ethanoic acid after this reaction is going to go down to 5.5 moles. And then we will produce salt in this reaction, and the ratio will be 1-to-1. In other words, however many moles of strong base we add, that's the number of moles of salt that we produce. And so it's 0.5 here, so the salt will go up by 0.5 moles, and so we will have 2.5 moles of A minus after this reaction has occurred. And then it's a weak acidic buffer, so we need to substitute these values into the Ka expression and rearrange it, or I'm using my rearranged form of the Ka expression here, and I can substitute these mole values straight in because the units are going to cancel out. And so the hydrogen ion concentration is 1.74 times 10 to the minus 5, that's the Ka of ethanoic acid, multiplied by the moles of the acid, 5.5, divided by the moles of salt, 2.5, and therefore the hydrogen ion concentration is 3.828 times 10 to the minus 5 moles per decimeter cubed. And this then gives us our hydrogen ion concentration. We've been asked to work out the pH of this buffer solution, so we need to take the negative log of this hydrogen ion concentration to find the pH, and that gives us a pH of this buffer solution of 4.42. Okay, that's the end of this video. Thanks for listening.